All right, I'm Jacob.
I'm Ben.
I'm Giovanni.
All right, and so what we kind of had is the measurement at the nanoscale. And so I'm assuming a lot of parents don't really know what nano means. It's essentially really, really small. So a nanometer is 1 times 10 to the negative 9th meters. And so nanoscience, we're working with 1 to 100 nanometers, which is extremely small. It's smaller than the wavelength of light. So that's just something to say. But the reason we use nanoscience is, as we mentioned before, there's a lot of medical and technical uses for it. So we already talked about the gold nanostars with cancer, and you can use that to essentially melt the tumors, which is really cool. At least that's what I thought. And then tech, you use that a lot in phones and other different things. Sorry. And then, whatever. Anyways. But another thing that's really interesting about nanoscience is that when you get to the nanoscale, a lot of materials are really different from their bulk counterparts. So things that you make on the nanoscale are normally, at least from what I've learned in the past week, they're supposed to be a lot stronger, but also a lot lighter. And so that's how we're kind of manipulating the different particles to hopefully benefit us.
Okay, so in this drawing, there's a diver, and he's entering the water, okay? And so what we thought the main concepts was diffraction and amphiphilic molecules. So diffraction is displayed as the sun, which is our source of light. You can see a physical wave passing through the object, and it spreads out inside the water. And so diffraction is when light passes through an object that it interferes with and interacts with it, and it spreads out like this. And so amphiphilic molecules are represented as he enters the water because the water doesn't touch him, and then he pops his head out. And so amphiphilic molecules are polar, which means they have a hydrophilic head and hydrophobic tail. Hydrophilic is derived from Greek, which means water-loving, and hydrophobic is also derived from Greek, which means water-fearing. And so the hydrophobic part can be demonstrated by the water not touching him going around as he dives in, and then he pops his head out, and it's not making contact with the water because it's hydrophobic. And it also can be just demonstrated by him saying, "I need air."
Yeah, as I'm going to elaborate on what Giovanni said with amphiphilic molecules. So the amphiphilic molecules have hydrophobic tail and a hydrophilic head. And so one side is attracted to water, which is the hydrophilic head, which is caused by having a positive charge, but the other side is a negative charge, so it needs to be in the water or be out of the water. And so this causes things to undergo self-assembly, which is when they automatically position themselves to be in a uniform sort of pattern, I guess, if you're speaking in bulk terms. And so these amphiphilic molecules can sometimes be used as capping agents, as one of the earlier groups mentioned, can be used to coat medicine in order to go into the body and not interact with other molecules, and that can destroy cancer cells. And with the diffraction, so the light is passing through the body and it's causing the light to spread out. And this can be explained by using wavelengths of light. There are 2 types of interference with the wavelengths. One is called constructive interference, where the wavelengths of light match up with each other to strengthen the effects. So that's what's demonstrated by all the lines that are visible. And the parts that aren't visible for you to see is destructive interference, where the wavelengths don't match up. And so they kind of cancel each other out. Like if you have a 1 and the -1, it'll just make a 0. Yeah, that's it. Thank you.
Questions? What experiment did you guys do to prove this application?
Okay, well, so for the amphiphilic molecules, we conducted an experiment where we had a tub of water, and what we did was we sprinkled the top with a thin, fine film of baby powder to show us the changes that occur. And so what we did was we created an olive oil. We mixed olive oil with some ethanol to dilute it, and then we poured that mixture onto the surface of the water, and the baby powder spread out so we could see how large our diffusion of the oil over the water, how large it was. And so this demonstrated that the oil was hydrophobic because it never fully mixed with the water. And what happened was it actually expanded and then contracted. And so we had to measure it when it was the largest to show the thickness of the oil molecules. And then how we measured diffraction was we had little lenses that we would shine lasers through, and it would put a pattern on the ceiling, because on the nanoscale there was little grooves in it that would scatter the light in a specific pattern depending on the engravings on the lens.
Hello, sorry. I have two things kind of. One's a question, the other's a little bit of a correction. So you guys kept mentioning, what was it, hydrophilic heads and hydrophobic tails, right? So which one has the charge on that?
The hydrophilic side has a positive charge, I believe, if I'm not mistaken. And the hydrophobic has a negative charge.
I think one of them doesn't have a charge, right?
So wait, what did you just say?
Oh, what I was going to say is I think one of them has a charge, one of them doesn't.
That's correct.
I want to say, I'll just go off of what he's saying because I'm not entirely sure which one has the charge. I'll just go with hydrophilic has the charge.
Yeah, and no, it's
And
okay. Like these things get confused so easily, especially in like our Gen Chem classes. So like it's very common. But you guys, the charge goes to the hydrophilic. Hydrophobic doesn't have a charge, right? Okay, so now for my question. I'm sorry. So you guys mentioned like constructive and destructive interference. Could you see a problem with the analogy in this case with using the sun for constructive and destructive interference?
I do see a problem with it because first of all, there's not really a general pattern to the light diffraction, but also the diver, he's more of a solid object and you don't really see any sort of grading, and so there's no light that actually passes through him.
Does the sun destructively interfere with itself ever?
No, there's no constructive or destructive interference.
Yes. So that's like my main thing here. Thank you.
Any other questions? Oh, is there one more?
What's their score?
Hopefully good.
That's a great question. They will find out their score in a few weeks when summer session sends them their grades. But they're doing well so far.
How can this work to cure cancer again? Like, can you explain that?
So the nanostar treatment? Yeah. So this hasn't been put into action yet, but theoretically what you could do is, so you create nanostars using two different solutions. I think we used some sort of citrate solution, and I can't remember what the other solution was, but you use that to form the nanostars, and what you do is, I'm not entirely sure how, but they're able to direct the nanostars through the body, and the nanostars latch on to the tumor, and then when they use the infrared light on the tumor, then the nanostars heat up, essentially melting the tumor.
I'm not actually, just to add on, I'm not actually sure if people have done this treatment with nanostars. They might have. I've seen it with nanospheres and nanorods that all have the resonance with IR. I don't think that the stars would because of their size and their shape, but I mean, I don't think that they would. I haven't seen it, but there might be some other treatment that you could do with nanoparticles of that shape. So, all right, would the artist behind this drawing also please stand up so we can acknowledge their nice work? Derek, very nice.